Well, I hope that you all came to the same conclusion that I did, that it looks like the value of b, which we knew was going to be somewhere between 2 and 3, but seemingly closer to 3, that makes this limit equal 1, in other words, makes this derivative very, very clean, is e, this number that we saw the first week, 2.71828182845. So let's remember how we defined that. We defined it as, that was when we were doing that compound interest problem, right? That was continuously compounded more and more and more frequently. We defined e as the limit as w went to infinity of 1 plus 1 over w to the w. At that time we used the letter n. I switched to w here because we're going to have h's. I don't want to have h's and n's in the same problem. So let's see if we can solve for the w. This is for the b, that is to say. We want to solve for the b to make this limit equal 1. So algebraically, we want to get this b by itself. So we want to move everything else to the other side. First, we'll move the h to the other side. So the limit as h goes to 0. We're going to have just b to the h minus 1 on this side. And since I'm going to have an h on this side now, I need to put a limit over there as well. Before, when I had the 1 over there, 1 wasn't changing, but now we have to put the h over there. And then, since we're trying to solve for b, our next step should be to get rid of the 1. So the limit as h goes to 0. Now we just have b to the h on this side. And I need to add a 1 to the other side. And remember, this is what we're aiming for. So we've got a 1 plus something. So it seems like it's working well. And now what do we want to do to get b by itself? At this point, a lot of people say, let's take a log. But is that really what we want? We don't want to get the b inside of a log. Imagine that h were, say, 3. You've got b cubed on this side. What would you do to get b by itself? You would take the cube root, right? In other words, raise each side to the 1/3 power. So that's what we want to do to get b by itself. Raise each side to the 1 over h power. At which point, there'll be no h's on this side, so I don't need the limit anymore. So b now will be the limit as h goes to 0, 1 plus h to the 1 over h. Huh. That looks sort of like what we've got here, but not exactly. But it's not apparent whether they are or not the same thing. This might be this in disguise. So one thing that we can do in math, as long as we do it consistently throughout the problem, is replace one variable with another variable in a different form. So if I make the substitution here and I say let w equal 1 over h, right? Because I really wish I had a w up there. So let's see what happens. I've got a limit, 1 plus, we're going to figure out what the h is. W is 1 over h, so this is going to become w. Now what have we got in here? We've got 1 over w. So if w is 1 over h, what's 1 over w? So this h is the same as 1 over w. So I can replace the h by 1 over w. So this is really looking good now, right? Because we've got 1 plus 1 over w to the w, exactly what we were hoping to find. The only trouble is here we have h going to 0 where we wish we had w going to infinity. So let's see if for this particular choice of w, when h goes to 0, does w go to infinity? So if you plug in a tiny, 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 tiny value for h, like 1 over 0.00001, what's going to happen to w? W is going to get very, very big. So as h goes to 0, it is true that w goes to infinity. So this is, in fact, e as we thought. So that's great. We have found the one magic special number where the derivative of b to the x is exactly b to the x itself. So we've proved that the derivative of e to the x is itself. And I hope you find that at least a little intriguing. This number e came up in a completely different situation where we were compounding interest more and more and more frequently. And we discovered that as we did that, we got closer and closer and closer to a balance of $1 million dollars in that particular example at the end of the year. Now, in a completely different context where we wanted to find out the function, the exponential function that is its own derivative, here e comes up again. Who would ever guess that there would be any connection between those two problems? But there it is. In fact, you should keep your eyes open. We'll start to see e again later this semester in other interesting places. Now, what we still haven't said is what about those other what about those other bases, like 2 to the x, 3 to the x, 4 to the x? Some of you might have recognized what those ugly constants were, especially the one for 2 to the x, where we got 0.693. Anyone recognize what the 0.693 constant was? If you said natural log of 2, you were right. So in fact, it's true that the derivative of b to the x is b to the x natural log of b. And the proof of that is coming next week. But just like with our power rule, we're going to use this rule now, and we'll prove it fully next week. So when we did 3 to the x on the board, the derivative of 3 to the x was 3 to the x, and we wrote 1.09 something. That 1.09 was natural log of 3. 4 to the x was 4 to the x times 1.38. 1.38 was the natural log of 4. And now that we've got these rules, let's practice with them. So let's try to take a few derivatives here. So we've got our function x to the 10 plus 10 to the x plus e to the x plus e to the 10. So remember, we've got two big rules now. We've got the power rule, which we use when we have a variable raised to a number, and we have the exponential rule, which we use when we have a number raised to a variable. So it's important to keep track of which is which. So this x to the 10, which rule should that be? Should that be our brand new rule for exponentials or our slightly older rule for power functions? So if we look at this, we see the x is in the base, which means this is not an exponential function. So this is our old power rule. The derivative of x to the 10 is 10x to the 9. Now when we go to 10 to the x, we see the variable is in the exponent. That fits our definition of an exponential function. So now we use our new exponential rule, which says the derivative of 10 to the x is 10 to the x ln 10. So don't be tempted to try to apply the power rule to this and somehow bring the x down and make it to the x minus 1. The power rule doesn't work for that. Power rule works when you have x raised to a number. This is an exponential function. E to the x, we just came up with that lovely proof that the derivative of e to the x is itself. So that's its own derivative. And what about e to the 10? Is the derivative of e to the 10 e to the 10? Tempting to say that, but let's look for where the x is. There is no x. E to the 10 is a number, right? E is some number between 2 and 3. If I raise a number between 2 and 3 to the 10th power, I just get another number. It's a big number, but it's still a what? It's still a constant, and the derivative of every constant is 0. So that is, derivative of e to the 10 is just 0. How about this one? Y equals 4 times 3 to the 2x. So just as we found with power functions, this isn't exactly in the format we want, right? We don't want 3 to the 2x. We don't know how to handle that yet. We only have a rule for something raised to the x. So we need to use one of our exponent rules from the first week to rewrite this before we take the derivative. So we can rewrite 3 to the 2x as 3 to the 2 to the x. That's what one of our exponent rules says. So then this is really just the same as 4 times 9 to the x. And now we are able to apply our exponential rule because we really do have just b to the x. 3 to the 2x, we don't have a rule for handling that as written yet. We need to rewrite it as 9 to the x. So we've got this constant 4. Sometimes constants disappear, like e to the 10 when we take the derivative. Sometimes they stay. Is this one that stays or one that goes? This is a multiplying constant, so we do our constant multiple rule, one of our 3 big rules from the start. It stays, and then it says take the derivative of 9 to the x, which we've just figured out is 9 to the x natural log of 9. And let's do one more. How about y equals 10 to the 2 plus 3x? So just as in part B, this doesn't look like the form that we want it in, but with our exponent rules, we should be able to rewrite it in a way we like. So, you might like to pause the tape as we suggest and see if you can figure out how to rewrite this. So we can use our exponent rule to break this up into this. I think that was our very, very first exponent rule from the first week. And so this is good now. We like having 10 squared out front. That's a constant. We know how to handle that. But we don't like 10 to the 3x. We just want something to the x. But we can rewrite that as 10 squared times 10 to the 3 to the x by our third exponent rule. And 10 to the 3 is just another way of saying 1,000. So we've got 100 out front times 1,000 to the x. And remember, there's no way to combine these two together. Right? Order of operations say you do the exponent first. So you do this, and then you multiply. There's no way to simplify that. And now we take the derivative. So our constant multiple rule says the 100 stays there. And then our brand new exponential rule says that the derivative of 1,000 to the x is 1,000 to the x times natural log of 10. And let me just remark that it's no surprise that the rule for the derivative of b to the x contains b to the x in it. Because remember, an exponential function is one that grows at a constant percentage rate of change, meaning that its rate of change is proportional to the amount that you already have. That's exactly what this is saying. Derivative is the rate of change. It's proportional, with this particular constant proportionality, to how much we already have. So if this were, say, the population of something, obviously growing very, very fast, then the rate of change of it is proportional to how many people you already have, which is exactly what you expect for an exponential function because you're growing at a constant percentage of your current quantity, your current population. All right, now that we've understood the basics of exponential derivatives, we've got a check your understanding for you to try on your own.